Hello, I'm Mladen, and I'll be presenting this joint work with Prashant, Patrick, and Matthew about mitigating topic bias when detecting decisions in dialogue. So here's a little bit of motivation for this. So why are decisions important? There's lots of data available, like recordings of, like audio, video recordings of meetings, and also transcripts, and there's a lot of meetings happening every day. So keeping track of decisions, why they came to be the way they did, and what would it maybe the alternatives, is becoming increasingly important to sort of when a certain period of time passes and we want to know how some decision came about. It's very useful to have an easy way to go back and sort of see in the meeting where it was made, how it was made, and why. And this is very useful for analysis. The goals of this paper is to see whether in this data set that we're using there's topic bias, so whether when models make decisions, whether they make them for the right reasons. That would be like the second thing, and also to see whether we can sort of fight this, if there is bias, whether we can do something to make it to alleviate. What's not our focus in this paper is to get maximum performance, so it's not the idea to get the best performing model ever, but just to analyze bias, and also exhaustively comparing ML models. So we use one model based on BERT, and it's possible that other models might have given us different results. This is something that still is left for future work to extensively experiment. So this is like a preliminary analysis. So what are decision dialogue acts? These are specific dialogue acts that indicate decision making, and in our data we have raising of an issue, proposing a resolution, restating a resolution, and agreements. And here are some examples. The examples are from all of the meetings that we have in our data, as you will see in the next few slides, are about a team that's concerned with designing a remote control. So this here is part of discussion about what material to use to make the remote control. Also, we merged this resolution, these two resolution classes. They're quite similar, and the restatement variant is much less frequent. So this was not very well lined up with using the BERT and deep learning models. So we just merged these two classes to have a little bit more training examples for this combined class. So the data we use from the AMI corpus, there's a small portion of it, 17 meetings labeled with these decision dialogue acts, or DDAs. These are just meetings performed by actors about designing a remote control. The data is a list of utterances, a dialogue, and each dialogue has to be classified as one of the DDAs or none of them. And only 4% of the utterances are actually labeled as some DDA. So what we're wondering now is whether there's topic bias in the data and the models. So basically, these topics, specific words like materials, case, plastic, and wood, these are words that basically they're not indicative of decision making in general, but they are indicative of decision making in this particular data, because these are all very key components of remote control design. So these words will often co-occur with like decisions, because these are things that decisions are often about. So what we were wondering is whether when we train the classifiers, whether they will pay more attention to the actual decision-related words or to these sort of topic-related words that are sort of correlated with decisions, but they are not. They would not generalize well to a different domain. So this is something we wanted to investigate. And to do that, we first needed a set of topic words. So a set of words that are very specific for designing a remote control. And we did this manually. So we just went over the entire data and we read it. And every time we saw something that seemed like a very domain specific word that's decision, that the decision might often be about, but only when talking about remote controls, we just added it to the set of topic words. And such words are often related to the material of the remote control, the shape, power source, and so on. So after having this set of topic words, then we did word masking, which basically means that we just removed so we have two versions of the data, the original one and the masked one. Then the masked one, we remove all of the topic related words from the set that we manually compiled. And by masking, there are several operations here that we could do when masking. We could just remove this word, we could replace it with a placeholder token, or maybe with a special token that's the mask one from Bird. We tried different variants, and finally the thing that worked better is just to remove the words. And this is also good because it's applicable to both the baseline model and the Bird model, while the let's say the mask thing is only applicable to the Bird model. You'll see soon why. So we have these two versions of the data, and now we just apply the model to both of them. We have two models. The baseline model is just a logistic regression on lexical features, and we have this Bird LSTM model, as we called it. So basically, it takes all the utterances in a window around, so let's say the utterance N is the utterance of interest that we want to classify. So it generates a Bird representation of all the utterances within a fixed size window of that utterance N that we're interested in. So we have these Bird representations for each utterance. These are representations of the entire utterance, so not of the tokens, but of the entire text. And then this sequence of utterance representations goes into a bidirectional LSTM. So we get another sequence of vectors, and each of those goes into into 3 linear layers, each of them making a binary decision for a particular class. And we did it in this way because sometimes it's possible that the same utterance is at the same time in several classes. So it's a multi-label problem, actually. This doesn't happen very often. It happens very, very rarely, but it can happen. So that's why the model works this way, instead of just having like a softmax over 3 classes. So basically we get 3 outputs, and for each one, if it's above, so they don't sum to 1 because these are 3 independent linear layers. And so each one that is above 0.5 is considered to have been classified into that class. So for example, this first utterance would be classified into the class R, the second will be classified into class I, and the third will be classified as both I and A. But when looking at utterance N, then we just throw away the predictions for all the other utterances in the window and only actually use the output for this utterance N. And then this is the loss function, which may look complicated at first glance, but it's just the sum over all classes of the sums over all possible positions of this window times the sum of all tokens within the particular window, and then just the cross entropy between the expected output and the correct, the obtained output and the correct output. We have 2 evaluation metrics, the utterance level evaluation and the segment level evaluation, with the first one being calculating the lenient form of F1 score on the level of each utterance individually. So we get a score for each of the 3 classes, issue, resolution, and agreement, while the segment level evaluation operates just on splitting the entire meeting into 30-second segments, and then looking whether there's any sort of decision-oriented activity in a particular segment. So it doesn't look at the particular class, but only whether any of the classes appears, and then looks at the overlap between the correct set of segments from the gold labels and the one that's induced from the model labels. And then there's an F1 score variant on these sets of segments. Here are the results. If we so this is the 3 classes: issue, resolution, and agreement, and this is the segment level evaluation, which looks at like all the classes at the same time. These are precision recall and F1 scores for the baseline model and for the BERT model. And the left part of the table is without masking, and the right part is with masking. So in the left part, this is on the original data, while on the right part, it's on the data where the topic words were removed. So as you would expect, the BERT-based models compared to the baseline models when using the same data do perform a little better and sometimes a lot better. So this is quite expected, I suppose. But the more interesting thing is that if you compare actually the models on different data sets, so the baseline model on the original and the masked version, then the baseline usually has comparable performance, but a little bit worse. While the BERT, for BERT, it's the other way around. So BERT usually benefits from masking, which would imply that BERT is able to somehow leverage the absence of topic words better, while the baseline model wasn't really able to. I'm sorry. And the image in the lower part of the screen is actually really just the data from the table just visualized. So for the different setups, if it's easier to follow that way. But the interesting thing here is that we had a look under the hood. So we don't see like massive differences in performance, but this is actually surprising because we removed a lot of words. So when we're removing topic words, the model has like a significant portion of its data removed, and yet it doesn't perform much worse. In case of BERT, it performs even better. So this would imply that it is able to generalize a bit better, perhaps. And we went and tried to investigate this by looking under the hood using the line method. So the line method is just a model agnostic method that allows you to know to which words a model is paying attention to. It works for any black box model, including this one we have here. And as you can see from the images, the word, let's say the word decision. So when not doing masking, the BERT model is paying reasonably large attention to like the words print and chip. And these are both words that are topic specific. And in the second example, this is very obvious because the word backup is dominating the importance when the decision is being made. And then with masking, where words like chip, print, and backup as topic specific words have been removed, you can see that the model is paying much more attention to words like decision or are we going. So like phrases that indicated there's a particular sort of decision or proposed resolution or something like that coming very soon. So in this sense, for some examples, we believe that the bias problem is a bit alleviated. So perhaps this model would generalize better on maybe data from a different domain. But this is something we need to leave for future work. And basically, the take-home message is that this very simple and silly and stupid way of removing bias does work for to an extent for this particular data set and model. If you have domain-specific data and want the model trained on this to be a bit more general, then this might be a good approach. But in general, we probably need a much bigger data set with annotated decisions that has many diverse topics and much more data in it. And that would then just fix this problem by itself. And here are some other ideas for future work. One interesting thing to try might be pre-training language models with unannotated decision-oriented data. So if anyone has some ideas on how to like cheaply obtain large amounts of data that has lots of decisions in it, even if they're not labeled, maybe fine-tuning BERT on such decision-oriented unlabeled data might just make the model more sensitive to decisions and therefore make it perform a bit better. That's at least the intuition. So yeah, thanks for the talk. If you have any questions or follow-up questions, just feel free to contact us by mail or reach out in some other way. Okay, thanks for your attention and enjoy the rest of the conference.